Oikos presents 15 Seconds of Strength.
Here we go. Steve's got a trunk full of groceries and no one to help him.
Oh, that's tough, Jim. Looks like a 5-trip load at least.
He grabs the first bag, the second. Bob, it looks like he's trying to do it all in one trip. He shimmies the door open, steps over the dog, and he stumbles.
Oh, right into the kitchen without missing a beat. Jim, now that's a man who eats his protein-packed Oikos.
With 15 grams of complete protein in each cup, Oikos Triple Zero can help build strength for every day. Oikos, stronger makes everything better.
Step into the world of power, loyalty, and luck.
I'm gonna make him an offer he can't refuse.
With family, cannolis, and spins mean everything.
Now, you wanna get mixed up in the family business.
Introducing The Godfather at ChumbaCasino.com. Test your luck in the shadowy world of The Godfather slot.
Someday, I will call upon you to do a service for me.
Play The Godfather now at ChumbaCasino.com.
Welcome to the family.
No purchase necessary. VGW Group. Void where prohibited by law. 21 plus. Terms and conditions apply.
Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. This week in astronomy, Venus Crust, Hidden Rogue Planets and LUGO mission. Venus crust may be active without plate tectonics. New research into the geology of Venus has revealed surprising insights into how the planet's crust behaves and evolves, offering a fresh perspective on the internal dynamics of Earth's closest planetary neighbor. Traditionally, scientists believe that Venus's crust should grow increasingly thicker over time. This expectation was based on the long-held view that Venus, unlike Earth, lacks the geological mechanisms, like plate tectonics, that recycle crustal material back into the planet's interior. On Earth, large plates of the rocky outer shell shift slowly, colliding and sliding past one another in a complex dance known as plate tectonics. When two of these plates meet, the denser one is often forced downward into the mantle in a process known as subduction. As the subducting plate sinks, it experiences intense heat and pressure, undergoing metamorphism, changes in mineral structure and composition. This not only reshapes the crust but also fuels volcanic activity and helps regulate the planet's crustal thickness. Venus, in contrast, does not exhibit clear signs of plate tectonics. Its surface appears to be a single, continuous shell without the massive moving plates seen on Earth. However, recent modeling by researchers, including those at NASA's Johnson Space Center, has challenged the notion that Venus's crust remains stagnant and endlessly thickens. According to the study, published in Nature Communications, the average thickness of Venus's crust is around 25 miles, 40 kilometers, and in some areas, it reaches no more than 40 miles, 65 kilometers. This finding is unexpectedly thin, especially considering Venus's intense surface temperatures and pressure. The models suggest a mechanism that, despite the absence of tectonic plates, still causes the crust to undergo metamorphism. As the crust accumulates and thickens, the lower layers eventually reach a density so high that they either sink into the mantle or become hot enough to melt. This process mimics aspects of subduction, in that it allows surface material to return to the planet's interior. Such recycling of crustal material plays a crucial role in driving volcanic activity on Venus. When dense rocks from the bottom of the crust either detach or melt, they release water and other elements back into the interior. These components can lower the melting point of mantle rocks, encouraging magma formation and possibly triggering volcanic eruptions. This discovery introduces a new way of understanding how Venus might remain geologically active without Earth-like plate tectonics. It shifts the focus from traditional tectonic mechanisms to density-driven processes that still lead to metamorphism and crustal recycling. Understanding these internal processes is vital to grasping the larger picture of Venus's geological and atmospheric evolution. The interaction between the crust, interior, and atmosphere of the planet likely shapes not just surface features but also atmospheric chemistry and climate. Researchers are now looking to future missions to gather direct evidence of these processes. NASA's upcoming Da Vinci and Veritas missions, along with the European Space Agency's Envision mission, aim to explore Venus's surface and atmosphere in unprecedented detail. These missions are expected to provide crucial data that could validate or refine the current models, offering a clearer view of the planet's active geology. There remains much to learn about Venus, particularly its volcanic activity. While current models and studies point to significant volcanism, the actual extent of this activity is still uncertain. Only with more direct data will scientists be able to determine the true nature of the geological forces at work beneath the planet's thick, cloud-covered surface. This new research has opened the door to a deeper understanding of Venus, suggesting that even in the absence of familiar Earth-like plate tectonics, the planet may possess its own unique and dynamic system of internal renewal. Roman telescopes set to uncover hidden rogue planets. Over the past decade, astronomers have grown increasingly fascinated by rogue planets, worlds that drift through the galaxy untethered to any star. Unlike Earth or Jupiter, which orbit the Sun, these planets wander the vast darkness of space alone. Their very existence raises fundamental questions about how planetary systems evolve and what kinds of forces shape their fates. The upcoming Nancy Grace Roman Space Telescope is poised to dramatically advance our knowledge in this area. While detecting rogue planets is notoriously difficult due to their lack of illumination, Roman is uniquely equipped to reveal them in large numbers and provide insight into how they form, what they're made of, and how common they might be throughout the Milky Way. A recent scientific paper delves into how Roman will contribute to the study of these mysterious wanderers. Central to the paper is the concept of the free-floating planet mass function, which is a statistical tool used to understand the distribution of masses among rogue planets in the galaxy. This idea parallels the better-known planetary mass function that describes the distribution of planet sizes around stars. By applying a similar approach to rogue planets, researchers hope to determine how many of these objects exist, what sizes they come in, and how their population compares to that of planets that remain in orbit around their parent stars. What makes Roman particularly powerful in this mission is its potential to detect not just large, Jupiter-sized rogues, but also smaller, Earth-sized or even sub-Earth mass planets that have previously been invisible to astronomers. This capability would vastly expand the known population of free-floating planets, offering a more complete picture of their abundance and characteristics. Scientists are especially interested in understanding how these planets were ejected from their original systems. Planetary formation is a chaotic process. Protoplanets are jostled around by gravitational forces in young planetary systems, and sometimes the interactions are violent enough to fling planets into deep space. Roman could offer clues about how often this happens and under what conditions, particularly by comparing the frequency and mass of ejected worlds. Theorists estimate that rogue planets might outnumber those bound to stars, potentially numbering in the billions across the Milky Way. If that's the case, the galaxy could be teeming with icy, lonely planets wandering in darkness. These worlds, lacking the warmth of a nearby star, are thought to be frozen and inhospitable. Nevertheless, their presence is critical to our understanding of how planets form and what happens when those processes go awry. The challenge is that rogue planets are very difficult to detect, especially the smaller ones. Without the light of a parent star reflecting off them, they blend into the blackness of space. One of the most effective techniques available today is microlensing, where the gravity of a rogue planet passing in front of a distant star bends the star's light in a detectable way. This fleeting alignment causes a temporary brightening or wobble in the star's light, revealing the presence of the otherwise invisible planet. Roman's design includes a powerful microlensing survey called the Galactic Bulge Time Domain Survey. This survey will repeatedly monitor dense star fields toward the center of the galaxy to detect microlensing events, potentially uncovering hundreds or even thousands of free-floating planets. With this rich dataset, scientists hope to build a statistical map of rogue planet masses, distances, and frequencies across the Milky Way. Roman will be especially valuable in identifying low-mass planets that current telescopes are too limited to find. These smaller planets are particularly important because they help paint a fuller picture of planet formation and ejection. Their small size means they could be easily displaced by gravitational interactions, unlike more massive planets that would require much stronger forces to be ejected. Finding larger rogue planets will also help reveal what sort of dynamic upheavals are powerful enough to expel them from their star systems. In addition to microlensing, Roman will use another method called the transit method in its broader exoplanet search. This involves detecting dips in the brightness of a star when a planet crosses in front of it. While this technique is generally more useful for planets orbiting stars, it will complement microlensing data to improve our overall understanding of planet populations in the galaxy. Together, these methods will allow Roman to detect both bound and unbound planets, offering a uniquely comprehensive view. Although the Roman Space Telescope is still awaiting launch, its capabilities are already exciting astronomers who believe it will fundamentally reshape our knowledge of the galaxy's hidden inhabitants. Its ability to find and study rogue planets, especially those of low mass, will allow scientists to explore questions that have remained unanswered for decades. How common are rogue planets? What processes lead to their formation and ejection? And could they hold any surprises about the range and diversity of planets that exist in the universe? By filling in these blanks, Roman will not only deepen our understanding of planetary science but also offer a new perspective on the dynamic and often chaotic nature of planet formation across the cosmos. Uncovering the Moon's hidden history with LUGO. Some areas of the Moon have captured more scientific attention than others, especially as we look ahead to a future where humans may live and work on its surface. Yet there remain many mysteries hidden within the lunar landscape, particularly in lesser-known features like the irregular mare patches, or IMPs. These formations are scattered across the Moon and pose questions that science has yet to answer, especially concerning their origins and what they might reveal about the Moon's complex geological past. While traditional missions have helped build a foundational understanding of the Moon's topography, a new proposed mission known as the Lunar Geology Orbiter, or LUGO, aims to delve deeper into these puzzles and potentially shape the future of lunar exploration. LUGO is designed to closely examine both the enigmatic IMPs and the equally mysterious lava tubes, which some scientists believe could be prime locations for future human habitats. IMPs are especially intriguing because they represent volcanic landforms that are unlike most others on the Moon. They typically appear as topographical depressions, often several kilometers wide, and feature a combination of smooth mounds and rugged, block-filled floors. These patches are notable for having significantly fewer impact craters compared to the surrounding terrain, which raises important questions about their age. Are they remnants from the Moon's distant volcanic history, or are they younger than previously believed, formed by processes we don't yet fully understand? Answering such questions is a core goal of the LUGO mission. Alongside IMPs, LUGO will focus heavily on lunar lava tubes, underground tunnels formed by ancient volcanic activity. These structures could offer natural protection against radiation and extreme temperatures, making them ideal candidates for the site of future lunar bases. However, estimates of their depth, width, and overall stability vary widely, and current data is far from conclusive. That's where LUGO comes in. With its planned suite of 4 highly specialized instruments, the orbiter promises to gather unprecedented information about the Moon's subsurface and surface features. Central to this suite is a ground-penetrating radar, which will allow scientists to peer beneath the lunar surface and observe the structures hidden below. For IMPs, this radar could map the boundary between the surface regolith and the bedrock, revealing the underground architecture of these mysterious patches. When aimed at lava tubes, the radar would detect subtle differences in underground materials and cavities, effectively sketching out a subterranean map that has never before been possible on the Moon. Complementing this instrument will be a hyperspectral camera that collects data related to the age and composition of the lunar soil. By analyzing reflected light at many wavelengths, this camera can help determine not just what materials make up the regolith in and around IMPs and lava tubes, but also when those materials may have been deposited or formed. This information will be crucial for understanding how these formations evolved over time. To further enhance the mission's observational power, LUGO will also carry a narrow-angle camera and a LiDAR sensor. These two devices will work together to produce highly detailed topographical maps of the Moon's surface. The narrow-angle camera, in particular, is capable of capturing very high-resolution imagery, which can aid in determining the morphology and possible formation history of the IMPs and lava tubes. With these tools, LUGO will conduct multiple orbital passes over the 6 largest known IMPs, each spanning more than 1 kilometer in diameter. Smaller IMPs, additional lava tubes, and other unique geological features like lunar domes and floor-fractured craters will also be observed as secondary objectives. LUGO will not operate in isolation. Its goals are designed to align with and enhance other upcoming missions. For instance, NASA's Dimple lander is expected to analyze the age of lunar regolith through radioisotopic measurements taken at its landing site. The European Space Agency is planning a mission called Lunar Leaper, set to launch around 2030, which will carry a ground-penetrating radar of its own, though its surface-based design means it won't have the broad observational capacity of an orbiter like LUGO. Meanwhile, the Trailblazer mission, another orbital project, could help refine the spectroscopic analysis techniques that LUGO will rely on. While LUGO remains in the proposal phase and awaits funding approval, its potential scientific return is immense. If launched, it could revolutionize our understanding of lunar geology, providing high-resolution data that fills gaps in our knowledge and potentially guiding decisions about where to establish permanent human settlements on the Moon. The kind of insight it offers would go far beyond what current instruments can achieve, particularly in decoding the mysterious histories of IMPs and assessing the practical value of lava tubes. In the long view, the success of LUGO could very well influence the way humanity explores and inhabits the Moon, and the people who eventually live in lunar habitats may owe much to the discoveries it makes.
Step into the world of power, loyalty, and luck.
I'm gonna make him an offer he can't refuse.
With family, cannolis, and spins mean everything.
Now, you wanna get mixed up in the family business.
Introducing The Godfather at ChumbaCasino.com. Test your luck in the shadowy world of The Godfather slot.
Someday, I will call upon you to do a service for me.
Play The Godfather now at ChumbaCasino.com.
Welcome to the family.